about those that new category of black holes that are in the 150 solar mass zone. So if this were live, Jolien, I'd ask everybody to give you a warm welcome with applause, but I think we will just wave or clap as we can. And sometimes how open here I will, oopsie daisy, I will unmute. How do I unmute you?
I think I did it.
There we go. Okay, so you're unmuted. How open are you to taking questions during the talk? I think, well, how open are you to that? Let me ask you.
I'm good with that, but if there's questions, you might need to let me know.
All right. So if you have questions, please raise your hand and I will try to acknowledge that. But also, if I feel the discussion is going on too long, I want Jolien to be able to get to the end of what he's saying, so we may relegate it to afterward. And it would be good maybe if you have something to put it in the chat if you have a burning question. Okay, so Jolien, please go ahead.
All right, well, thanks. And I wish I could be there with you. It's always nice to visit Waterloo, but thanks for that introduction. So what I want to talk about is the LIGO and Virgo observations of gravitational wave. The first direct detection of gravitational waves was about 5 years ago, five and a bit years ago, which is approximately one graduate student generation. So this whole field has really exploded in basically the time that my current graduating graduate students just were starting. So it's been quite an exciting time. So what I want to do in this talk is first start off by talking a little bit about what gravitational waves are and how they what they do, how we detect them, what produces them. And then I'm going to look at some of the detections that we've made. I'm going to cherry pick them. There's 50 now. I'm going to cherry pick the ones that I think are kind of interesting. And for each one, I'm going to say a few things about what we can learn about physics, fundamental physics, tests of general relativity, and also what we can learn about astrophysics, and such as the very massive 150 solar mass black hole that we discovered recently. But I'm not going to go over all 50. So let me start off by talking about gravitational waves and what they are. They're gravitational waves, and in GR, of course, gravitation is described as the geometry of space-time. So these are really just waves of geometry. And so to explain maybe what a wave of geometry is, I want you to imagine that you're standing here with the gravitational wave passing through you. And the effect of the gravitational wave as it passes through you is basically to change your proportions. So you might start off with your normal proportions, and then as the wave passes through, you might get a little taller and a little narrower. And then as the wave changes sign, as it passes through, you might get a little shorter and a little wider. Now, there are gravitational waves passing through you all the time, and you don't really notice this effect happening. And that's because the amount of distortion, which we call strain, which is the fractional change in your length, is only about 10 to the minus 21. So 1 part in 10 to the 20. So it's an incredibly small effect for most of the gravitational waves that are passing through you. And to give some context, that means that if you were trying to measure the distance to Alpha Centauri, a gravitational wave might change that by about a hair width. It's going to become important later, so I'll just mention that in general relativity, there are two polarizations of gravitational waves. So just like in Maxwell's electromagnetism, there are two polarizations of photons. There are also in general relativity two polarizations of gravitons. We call one the one that stretches you vertically and horizontally, the plus polarization, and the other polarization sort of is the same pattern but rotated at 45 degrees. All right, so two independent polarizations of gravitational waves in general relativity. To detect these, it's a very small effect, but we use basically something going back to the 19th century where the ether of electromagnetic waves was attempted to be detected using an interferometer. So basically, the idea is that you take light, we now use a laser, you split it with a beam splitter into two arms. The light is reflected back from the arms, recombines at the beam splitter. If the arms are the same length, then the light all comes back towards the laser and none comes back towards this anti-symmetric port. But if a gravitational wave passes through, it will be stretched in one direction, squeezed in the other direction. That will lead to incomplete interference, and a small amount of light might trickle out to the photodiode. So that's the basic technique for how we detect these things in LIGO. Now, because the effect is so small, we need and because, well, the fractional change in the length is so small, what we try and do is we build very long arms so that the actual change in the lengths of the arms can be measurable. So here are the currently operating kilometer scale gravitational wave detectors that have been used in the first three observing runs. So here we see the LIGO Hanford Observatory in Washington State, and these two interferometer arms stretch off 4 kilometers long from this central station where the beam splitter and the laser and such are. The LIGO actually has 2 detectors, one in Washington State, the other in Louisiana. And in addition, a few years ago, the Virgo detector began operating alongside with LIGO detectors. This is located near Pisa in Italy. And then just very recently, this underground detector in the Kamioka mine in Japan called Kagra has started operating. So these are all 3 or 4 kilometer large arms. Gravitational waves are produced by massive objects that are moving. In an analogy with electromagnetic radiation, where you produce electromagnetic radiation by shaking an electron around, you produce gravitational waves by shaking mass around. The difference is, though, that in electromagnetic radiation, you can produce a time-changing electric dipole simply by shaking an electron around. So the dominant radiation is dipole radiation, electric dipole radiation. In general relativity, because momentum is conserved, you can't actually produce a time-changing mass dipole. So the dominant radiation that comes from in general relativity is quadrupole radiation. You can have a changing mass quadrupole, and Einstein's famous quadrupole formula describes the amount of radiation that's produced by that. The canonical example of a system with a changing quadrupole might be a binary star system, where the two masses are orbiting around a common center of mass. All right, so what I've plotted here is the quadrupole, the leading order radiation in general relativity. This is the emission pattern that you would get from the plus polarization. So a lot of radiation towards along the axis of the system, a little less along the equator of the system. And then the cross polarization also has lots of radiation towards the axis, but no radiation along the equator. If you had a binary system that was radiating gravitational waves, then what happens is that as it radiates gravitational waves, it loses energy to the gravitational radiation. That energy comes from the orbit, which then decays. As the orbit decays, the two bodies start moving faster, just Kepler's law. The faster motion means that V over C approaches 1, so the speed gets larger and larger, and that amplifies the amount of radiation that you get out. And so the orbit gets driven smaller and smaller to higher and higher frequencies and higher velocities until the two bodies merge. And if they're black holes, then they would ring down and form a final black hole. All right, and so you can see that in the waveform that you expect to get from this process. So what you see is the strain produced by this orbital motion. It actually comes out at twice the orbital frequency for quadrupole radiation in a circular orbit. And you can see that it starts off at comparatively low amplitudes and low frequencies, and then as the orbital frequency increases, the amplitude increases and the frequency also increases in this chirp-like behavior. Peaks at the merge at the moment the black holes merge, and then decays exponentially during the ring down. Okay, so that's basically the system that we observed 5 and a bit years ago on September 14th, 2015, when we detected the very first detection of gravitational waves, and it came from a binary black hole. And it was pretty surprising. We had just started operating the advanced detectors. This was like hours after we started, and we got this incredibly strong signal. And it was surprising. Well, it was a great confirmation of Einstein's theory that we detected the gravitational waves. It was also the first time that we ever saw a binary black hole, certainly a stellar mass binary black hole. I think until then, it wasn't clear that such things actually merged. But this was the first binary black hole merger that was discovered as well. And here, I'm showing the actual signal that we saw in the LIGO detectors. There's two things superimposed here. That this time series down here, so time's running along the horizontal axis. This time series here shows the strain that was measured in the detector, and you can see that it starts off sort of low amplitude, low frequency oscillations, and ramps up to higher amplitude and higher frequency. What's my pointer? Up here, and then some sort of merger. So that's what these sequences are for Hanford and Livingston. In behind, I have a spectrogram where the horizontal axis is time again, and the vertical axis is the frequency of the gravitational waves. And here, and then the brightness is the amplitude. So here you see that it starts off at low frequency, sweeps up over a tenth of a second, a fraction of a second in frequency, and gains strength and increases in amplitude as well. So this is the kind of chirp-like behavior that we expect from the quadrupole radiation from from these binary black hole systems. So this plot here shows all of the events that we have seen to date, or reported to date, beyond, well, including that very first one. On the vertical scale is the mass, and each one of these mergers has two companions, two black holes of different masses here. And for example, in this case, these two things merge to form this final black hole. The blue things are all black holes. The orange things are neutron stars. So we've seen a bunch of black hole mergers and a couple binary neutron star mergers so far. And as I said, I'm going to cherry pick a few of these to talk about. I'm not going to talk about all 50, but they all have their own stories. But let me start off by talking about the binary black hole mergers. So the first one I already talked about was our first detection, GW 150914. And the next one I want to talk about is something that happened during our second observing run, so a few years ago. This is on August 14th of 2017. And what's interesting about this event is that it is the first event that we saw after the Virgo detector joined our network of detectors. So it was the first event that was seen in 3 detectors. Previous ones had been only in 2 detectors, in the LIGO detectors. And this is actually going to allow us to make an interesting test of general relativity, which I'll have to explain first by saying that one thing that you can do when you detect things in 3 detectors is you can start to get an idea of where on the sky the source of the gravitational waves are. And primarily we do that with LIGO. LIGO sort of sees radiation coming from huge swaths of the sky. There's, a few null spots in our beam pattern, but basically we can see things coming from all over. So to figure out where in the sky source is, we have to use some sort of triangulation based on the time of arrival of the signal in each detector. So if we see a signal arrive in, say, Hanford, and then a few milliseconds arrive in Livingston, then that tells us that that signal might have to come from some ring in the sky. So some ring about the axis joining Hanford and Livingston that has a constant time difference between the arrival in one and the other. All right, so between Hanford and Livingston, we would be able to locate things to anywhere on the sky in that ring. And then because we have different sensitivity coming from different positions in the sky, there's some antenna pattern that we can use to restrict that a little bit. So this blue curve is what we would get with just Hanford and Livingston. But now if we add in Virgo, we've got two more time separations. So Hanford Virgo time separation and the Livingston Virgo time separation. And those form 2 more rings in the sky of possible positions. And these rings, so these 3 rings are going to intersect in 2 positions. So from the time alone, we could figure out that the source was either coming from that position or that position. And then when we fold in the response of the directional response of the detectors, we could figure out that, in fact, the source was coming from there. Now, this is going to come in very useful for multi-messenger astronomy when we want to find the source, when we want to follow up a gravitational wave signal with telescopes and look in a particular part of the sky for where that signal is. But But for the present purposes, this is a binary black hole system, which is not normally expected to produce light. What it allowed us to do was something rather different. And it let us test this prediction of general relativity that said that there were only two possible polarizations of gravitational waves, the plus and the cross, which I described earlier. Because in a general metric theory, if I didn't impose the Einstein field equations, gravitational waves could in principle have 6 polarizations. So if we look at this top line here, these are all transverse polarizations. So the effect of the gravitational wave operates transverse to the direction of propagation. So if it's coming towards you from the screen, the plus affects you laterally and the cross affects you laterally. But there's also this other mode. This is a dilational mode. So it either stretches you in all directions or squeezes you in all directions. It doesn't stretch you in one way and squeeze you the other. So that's called a scalar mode. These two are called tensor modes. Also, in principle, would be allowed longitudinal type modes. So now I'm imagining a gravitational wave traveling towards the right. And the effect of these types of polarizations, well, this one here simply stretches you and squeezes you longitudinally in the same direction as the wave is traveling instead of transversely. And then there are these two vector modes, which are semi-longitudinal, semi-transverse. Okay, so how does this help? Well, since we know where in the sky this source was, we can we can look at the response of our detector to different polarizations. So if the source was coming from over here, say, our detector would have a lot, and it was plus polarization, our detector would detect it. But if it was cross polarization, then it wouldn't. Whereas if it's over here, the plus polarization wouldn't detect it, but the cross polarization, but if it was cross polarization, it would. All right, the vector modes have different antenna patterns, and the scalar modes have yet a different antenna pattern. Now, we happen to know in this case, for all the different detectors, where in the sky relative to that detector this wave was coming from. And so we can look at the amplitude that we got in each detector and see whether it's more consistent with waves that are tensor in character, or vector in character, or scalar in character. And it turns out that the odds that it's tensor versus vector are something like 200 to 1, and tensor versus scalar is like 1,000 to 1. So this was the first time that we actually could confirm that the predictions of the general relativity, the Einstein field equations, that we only have these tensor polarizations. This is the first time that we could test that and confirm that prediction of general relativity. So this is a new test of general relativity. Okay, the next source that I'm cherry picking is one from well, a year and a half ago during LIGO Virgo third observing run, and this was on April 12th, so GW 190412. And this is going to give us yet another test of general relativity that we were able to do for the first time. And the key thing about this event is that most of these events, the two different components, initial components, are roughly similar masses, but this one has a very different mass for the two different initial components. So this is a plot of the probability distribution of the mass ratio, the secondary mass to the primary mass there's two curves, there's two probability distributions, there's some waveform uncertainty. So these are for two different waveform models that we have. But it's pretty clear that the mass ratio is somewhere between 5 to 1 and 2 to 1. So there's quite a bit of difference in mass of these two components. So why does that let us do a test of general relativity? Well, I mentioned that the leading radiation, which is described by Einstein's quadrupole formula, produces these sort of radiation patterns, these quadrupole radiation patterns with frequencies that come off at twice the orbital frequency of the binary. Well, the next higher radiation mode would be octupole radiation. And this has never before been observed in gravitational waves. And there's a couple reasons. First of all, it's down by factors of V over C, so it's higher order in relativistic corrections, so that means it's weaker. But also, it's never been seen in things like the Hulse-Taylor binary pulsar, not only because it's not relativistic, but because the two components are relatively similar in mass, and the octupole radiation depends on the difference and is proportional to the difference of the masses. So it had never been possible in our previous detections to detect octupole radiation simply because the masses of the two components were rather similar, so the mass difference was little. The octupole radiation here that I'm showing would come off, instead of twice the orbital frequency, it would come off at 3 times the orbital frequency. And so this is for this event, this is the time frequency spectrogram that we observed. And we can see this track of quadrupole type radiation. So again, sweeping up with frequency and amplitude and time. And so what we do is, knowing the quadrupole track, we can then look for we can look for power along this m equals 3, so 3 times the orbital frequency track. And to do this, you actually have to, if you look at this diagram, you're not going to see it. This is very difficult measurement to make, but with detailed match filtering, we can actually pick out the m equals 3 radiation, and therefore confirm that there is in fact higher modes of radiation beyond the quadrupole. So that's also a new test of general relativity.
Sorry, a quick question. Which event did you detect this for?
This, I said, was 1904-12. Okay. That was the first time we saw it. We get actually a stronger signal from this one, which I'll talk about, because it's got even bigger mass ratio. Mm-hmm. But this was the first one. Okay, moving on to sort of more astrophysics, I want to talk about how we've now found compact objects in places where they shouldn't be. So there are a couple theoretical mass gaps in astronomy. The lower mass gap down here and the upper mass gap here. The lower mass gap is between whatever the most massive neutron star there can be, and the lightest mass black hole that can form, you know, in ordinary stellar evolution and supernova models. And so there's theoretical predictions that there should, as well as observational evidence, that there is this gap between the heaviest neutron star and the lightest black hole. There's also an upper mass gap here, which is which is a region between about 60 and 120 solar masses, where we don't think that we can form black holes through ordinary stellar evolution because of a phenomena called pair instability supernova, which happens in massive stars, massive stars of low metallicity. Basically what happens is that the cores of the stars are so hot that the photons that they produce can actually form positron-electron pairs, which can, if you form them in abundance, sort of sap the central pressure and cause the star to collapse, which would then lead to a runaway thermonuclear explosion that destroys the whole star and prevents black holes of certain masses from forming. Now you can see from this diagram that we've detected lots of black holes in this mass gap, such as this one. But you see that what it really is that there's these two black holes that were not in the mass gap, so perfectly allowed to form from stellar evolution, that just merged in the final remnant black holes in the mass gap. But I do want to call your attention to this event here that we saw, where in fact these original mass stars, or black holes, were sitting in the mass gap, and in particular this one's right in the center of the mass gap. And they merged and they formed this what we call an intermediate mass black hole. So bigger than what we would normally expect to see from stellar evolution. All right, so here's a plot of the probability distribution that we inferred for the mass of the primary and the secondary, and a two-dimensional probability distribution of mass versus mass. And you can see that the primary mass, the probability distribution, its mass is between 60 and 120. So basically, all of the probability lies in this theoretical mass gap. So this plot basically shows what kind of black hole mass you would expect to form from the normal stellar evolution supernova from a initial zero-age main sequence progenitor. So basically stellar evolution and supernova models. These different curves are for different metallicities. This curve here is the relevant one for low metallicity stars. And you can see that progenitors between here and here, so 120 to 210 solar masses, they don't form any black holes. So normally you would expect this place to be populated from collapses of these stars, but they undergo this pair instability supernova, and so nothing gets produced here. So this is where that mass gap is. But this is where one of our black holes was. Okay, so this is a mystery. We've seen something where it shouldn't be. So that means that we have to explain how could we have formed these things. And so there were several scenarios that we explored. One is hierarchical black hole mergers. So basically the idea here is, if I go back a few slides, we've seen that we can produce a lot of black holes. We can produce black holes in this mass gap through mergers of lighter black holes. So perhaps what happened is that we had two black holes that were below the mass gap that merged, formed something in the mass gap, and then found another black hole and merged with it. So this might be a second generation black hole merger. So that's one possible scenario. Another one is that maybe the progenitor stars, the stars that made the black holes, were in a multiple star system, and maybe two of these stars during their binary evolution merged, and somehow that messed up the stellar evolution sequence and allows black holes in the mass gap to form. So maybe it was a stellar merger prior to black hole formation. Another intriguing possibility is maybe these are black holes that formed in the accretion disk around a supermassive black hole in an active galactic nucleus. And if the black holes were formed there, then they could accrete matter from the disk and grow to the point in which they are in the mass gap. And then the black holes can migrate through the disk and sort of pile up and find each other, form binaries, and then merge. So this is another possibility, is that these are, that this is a binary system that was formed in an active galactic nucleus disk. And then we explored some alternative scenarios, but I think I am going to not say much about those. Could be an eccentric binary collision, which with waveform, so our waveform model might be wrong because there's eccentricity. It could be explained as a lensed event, gravitationally wave lensed event. And it could be explained by black holes that didn't form by stellar evolution, but in the early stages of the cosmological evolution of the universe. All right, I'm going to go on then and talk about the lower mass gap. And this event that was seen fairly recently, August 14th again, but now 2019. And this is an interesting event. Well, it has a very asymmetric mass ratio as well, but it's interesting because one of these components is sitting in this lower mass gap. So now we're looking at the secondary mass in this mass plane, and we see that it's most likely more than well, it's more than 2.4 solar masses, probably more than 2.5 solar masses. And this is more massive than we think neutron stars can be. So it's probably a black hole, but we're not sure. But if it's a black hole, it's sitting in this gap between the neutron stars and the black holes that we didn't think from our conventional supernova models that there should be anything. Alternatively, maybe it's a neutron star, but then it's more massive than any other neutron star that we've confidently determined what its masses are. And that would be peculiar too, because we also feel that think that the equation of state of neutron star forbid neutron stars to be this massive. So this is a curious event. It might be a black hole, it might be a neutron star. It's either the lightest black hole we've ever seen or the most massive neutron star that we've ever seen. And it might require us to reconsider some of the stellar evolutionary and supernova models that describe that lower mass gap. Okay, I'm going to, that's all I want to say about the binary black holes. I want to talk a little bit more about the binary neutron stars, because there's one truly fantastic event, which you've probably heard a bit about, but I think I want to talk about it because it's so amazing. This was GW 170817, which was the very first time we ever saw a binary neutron star merger. And what was particularly impressive about it, not only was it the very first binary neutron star merger that was ever observed, and here you can see the time frequency diagram in the gravitational waves that we observed, but it was also accompanied by a gamma ray burst. So here we see Fermi satellite gamma ray counts. And 2 seconds, a little less than 2 seconds after the merger, there was a gamma ray burst. So it's not only the first binary neutron star that was ever observed, but it's the very first time a gravitational wave observation coincided with an electromagnetic observation. So this is the first multi-messenger astronomy done with gravitational waves. Virgo was also operating at the time. And just like with the event, the August 14th event that happened just a few days earlier, we were able to time triangulate and figure out the location of this event in the sky. And this was very important in this case because it allowed telescopes, conventional telescopes, to start surveying the region of the sky where it was predicted to arrive from. And the kilonova associated with this was within a day identified, along with the host galaxy. And then over the next few days, this kilonova was seen to decay and redden. And that gave astronomers a lot of information about kilonova and the ejecta that's produced when two neutron stars collide. And it's now believed, in fact, that binary neutron star mergers is probably responsible for the nucleosynthesis that produces most of the heavy elements on the periodic table. So these blue elements here are formed from, regular supernova type processes, but the bright yellow colors here are elements that are formed mostly from binary neutron star mergers. So in particular, your typical Nobel Prize was forged by two neutron stars being merged. Another amazing thing that we were able to do is another test of general relativity with this. Because we received an electromagnetic signal and a gravitational wave signal within 2 seconds of each other, that means that we can figure out what the speed of gravitational waves are, which we've never known. We never knew what it was before. Basically, when the gravitational waves arrived, the gamma rays were 2 light seconds behind. And they had been traveling, we know how far the signal came from. They've been traveling for 100 million years. So the speed of gravity has to be the speed of light within about 2 light seconds in 100 million years. So this is the value for the speed of gravitational waves. It's the same as the speed of light to within perhaps a micrometer per second. Another interesting thing is that we can use this as a way to measure the Hubble constant. So what I'm showing here is Hubble's original Hubble diagram, where he plots the recessional velocity of nebulae or nearby galaxies in kilometers per second versus the distance determined by Cepheids, and then draws a line, and the slope of the line is the Hubble constant. So it's about 500 kilometers per second per megaparsec, which is not the right value, but the measurements were not that good back then. So we can now make our own Hubble diagram. We've seen the host galaxy, and that allows us to measure the redshift, which tells us the radial velocity. And for the gravitational waves from the amplitude, we have a direct measurement without any cosmic distance ladder of the distance. And so that is this horizontal line. And so we have a single point in the Hubble diagram, and we just draw a straight line through that point. And we compare that with the two other best estimates, one from supernovae and one from Planck observations of the cosmic microwave background. And we see that we're within our error bars, so we agree with both of them. So that's pretty exciting. We've just got one data point and it agrees. A couple interesting things is that we agree with both of them, but they don't agree with each other. There's some tension in the value of the Hubble constant. It should just be one number, but these two measurements give different numbers. So what we're hoping is with a few more observations, we can put a few more points in our diagram, reduce the error bar, and maybe help resolve this tension. All right, I guess one more thing I'd like to say in terms of fundamental physics is that another thing we were able to determine with this is the nature of very dense matter. So matter that is more dense, cold matter that's more dense than neutrons, than nuclear matter, only exists in the cores of neutron stars. It's the only place in the universe that exists, and we can't replicate it in the lab. So if we want to know what the universal properties of matter are at extremely high density, the only place we can find that is in a neutron star. And what we are mostly interested in for this matter, well, we're interested in what physical processes are going on, but the different models of nuclear matter give different predictions of what's known as the equation of state, which is the relationship between the pressure of the matter and its density. So here's all several different models from nuclear physics describing different types of different approximations of what this matter might look like, and they give different curves on this diagram. Those curves in turn determine the structure of neutron stars. So if I have a 2 solar mass neutron star made out of this kind of matter here, or this equation of state, then it will have a radius of 11 kilometers. But if it's way over here with this, if the true equation of state is this one over here, it'll be more like 15 kilometers. So the radius of a neutron star will depend not only on its mass, but on the equation of state. So if we can figure out the mass and radius of a neutron star, then we can then we gain insight into what kind of matter must be at its core. Well, it turns out with gravitational waves, we can actually make this measurement. And the reason is because as the neutron stars get close to each other, they exert tidal fields on each other, which distorts the stars. And in doing so, you deposit energy into the deformation of the star, which saps energy from the orbit and causes it to merge faster, basically. So we can measure the rate of the merging to figure out essentially the radius of these stars. So larger stars will distort more and will merge faster. So we did this measurement, and for the binary neutron star, and we were able to find probability distributions for the masses and the radii of the two stars, and that's what's shown here. And you can see that some of the equations of state curves, mass radius curves, are not supported by our data, whereas others are. So we're starting to learn something about we're starting to exclude stiff equations of state that would form large neutron stars, and favoring soft ones that produce smaller stars. And that tends to give us, it turns out, smaller upper bounds of neutron star masses. So these curves turn over at the largest neutron star mass. I think I'm running a little bit over. So I think maybe what I'll do is, unless people want to hear about it, I'll skip the second neutron star merger, and instead, there's only a couple slides on that. Come to my conclusion, which is that we've looked at a few of the 50 events that we've detected so far, but we've learned a lot of things, both about fundamental physics. We've done a direct detection of gravitational waves. We've done the first time detected post-quadrupole radiation. We've confirmed that the gravitational waves have tensor polarization. We've measured the speed of gravity, and we've measured the equations of state of cold dense matter. So there's a lot of fundamental physics that we've done, but also in astronomy. We've observed the first binary black hole merger, the first binary neutron star merger. We've found compact objects that are in theoretical mass gaps, which is interesting. So, and speculated about different formation channels. This is what I skipped, the unusually heavy binary neutron star. But we have done our first multi-messenger astronomy with both gravitational and electromagnetic waves. We've got some insight into what the origin of heavy elements are, and we've now have a new way of measuring the Hubble constant that doesn't depend on the previous cosmic distance ladders. So I think I've gone a little bit over, so I should probably stop now and take questions.
Okay, well, that's great. Let's silently applaud Jolien, I guess, if you want to hit the clap hands thing and the reaction, or us just do it visually if you're on screen. And I think we can certainly take questions now. Who would like to start? I think you need to raise your hand, I guess, for the questions here. So let me see if anybody, it'd be easier for me to follow it if you have a raised hand. I'll start, I guess. When you have that one, I think it was 1708-14, that's the one that was the first time that you confirmed tensor polarization. Is that right?
Yeah, that's right.
Okay. Are there other systems where you can repeat the test to really nail this down? I mean, I think it was chances of what, 1,000 to 1 for tensor or something, and or for scalar, I mean, and 200 to 1 odds against it being vector. But I'm just wondering if you can even more precisely nail this down with other systems, or if that's been done.
Yeah, actually, this 1708-17 was even better for this, because we knew exactly, because we had an optical counterpart, we knew exactly in the sky where it was. So that actually gave us better results. Now, there is a subtlety here that, well, there's a couple things limitations for that measurement. First is we only can compare pure tensor to pure vector, or pure tensor to pure scalar. So we can't rule out that there's a little bit of vector or scalar radiation, but mostly tensor radiation. So that's one limitation. And then the other limitation is that we assume that even though it might be scalar radiation, that our waveforms are correct. But if it wasn't general relativity, maybe our waveforms should be different. So there are limitations, and what we're trying to do now is remove some of those limitations. And to do the measurement really properly, we need to have at least 5 detectors in our network, so that we can isolate all the polarization content. And we really want to do sort of a null test where we subtract off any possible tensor radiation and see if there's just any radiation left. So we've started trying to do things more like that, and we get weaker constraints when we do those. But but I think what this is showing is that that there definitely is tensor. That's definitely at least mostly tensor radiation.
Okay. I guess I would have thought that, you know, with enough events, you could just beat down the statistics. And is that the way of thinking about how to deal with this? That the more events, the more you can rule this out? Or
yeah, I think that's that is going to be possible with more events. But again, we need to have a big enough network to be able to basically triangulate with the time. So we need to see it in 3 detectors, and then.
Okay,
So
thanks. Other questions or comments?
So I could ask something. So you mentioned about how, well, you mentioned how you've detected this, higher multipoles beyond the quadrupole. So what was the significance of that detection? And in the future, how will that improve?
So I guess the significance of that is simply that up until now, we had only confirmed that the quadrupole formula of general relativity was true. So the general relativity field equations obviously give you the quadrupole formula, and with the Hulse-Taylor binary pulsar, the fact that the quadrupole formula was correct had been, that's one of the famous tests of general relativity. But
I meant the detection significance, sorry.
Oh, the detection significance. Let's see. That the detection significance, it was, I think, on the order of 1,000 to 1 odds that the quadrupole is there. Again, what I said was with this event, my pointer's gone. With this event was the first time we did it. We actually get better significance with this event. So the Bayes factor for quadrupole, so if you compare 2 hypotheses, one that there's only quadrupole radiation in the universe, and the other is that there's quadrupole plus octupole plus higher modes, then I think it's 1,000 to 1 in favor of the higher modes.
And so if we start seeing more extreme mass ratios for future events, then we'll see these higher multipoles more significantly. Is that what you're saying?
Yeah, that's right.
And so in the future, are the improvements to the detectors going to make it easier to see these more extreme mass ratios?
Well, I think that the relative frequency of extreme mass ratios are probably going to I think it's going to be astrophysically limited mostly, that only a fraction have this extreme mass ratio. But we'll see more events as the sensitivity improves, so we'll be seeing more of them because of that. And also, as the sensitivity improves, the signal to noise ratio of the events will just get that much brighter, and we'll be able to, and these modes will stick up above the noise much stronger. So I think that most of it will be just improving the signal to noise ratio of the events that we do see.
Okay, thanks. We're a bit past 12:30, so we probably have to close off. Are there any other, maybe one more burning question if there is one? Because otherwise I think we do need to call this to a close. Okay, not seeing any. Well, let's thank Jolien again using our hand reactions and
thanks a lot, Jolien. That was a great talk.
Yeah, very good talk. Thank you. And we will, I guess there's another meeting in a week.
All right. Thanks for inviting.